Welcome back, AP Chemistry students, to Unit 5, Kinetics. Today we will be talking about Unit 5.4, Kinetics Cleanup. This lecture is relatively short as we've already gone over a large amount of it, but I just want to drive a couple points home. So when we talk about the speed of a reaction, we've mentioned how most half-lives are first-order reactions. However, we didn't really go into what a half-life was. So just to review from first-year chem, a half-life is the amount of time it takes for half of a sample to undergo some sort of decay or reaction. So to go from 100% of the sample down to 50% is some amount of time. And that time is constant. To go from 50% down to a quarter takes an equal amount of time. So when given kinetics problems and you're shown a graph like this, the first question you'll get asked is, hey, what is this order not? Obviously, since concentration versus time is not a straight line, we can definitely say this reaction is not zero order. It has to be first or second. And we might be asked to determine the half-life, in which case take your initial concentration, figure out how much half of it would be, and then find the amount of time it took to get there. That amount of time is the half-life. So if the question proceeds to say, what is the concentration after some interval of half-lives, you're just going to divide by 2 that many times, much like you did in first-year chemistry. If you haven't taken first-year chemistry, or if you do not know or remember how to find concentration after a set number of half-lives, in the description of this video, I will link to my half-lives video for first-year chem. So here's an example problem. We are given concentration versus time data, and we're asked to determine what order. Is it definitely not? Concentration versus time, if this was a straight line, would tell us it's zero order, but since it is very clearly not, this can't be a zero order reaction, since this is not a straight line. To determine the half-life, we start with 1 molar. Half-life would be the amount of time it takes to get to half a molar. So it looks as though the half-life would be 3 minutes. What would the concentration be after the second half-life? Well, after 1 half-life, we went down to a half a molar. So 2 half-lives would take us down to a quarter molar. Or you could have just looked on the graph. If it takes 3 minutes to execute a single half-life, it will take another 3 minutes to execute a second half-life. And so at that time, our concentration is a quarter. When would 75% of the sample have decayed? 75% of the sample decaying means that 0.75 molar has undergone decay, leaving us with a quarter molar of the original sample, which is what we got after 2 half-lives or 6 minutes. Half-life problems are usually in line with what you learned in first-year chemistry. They are this simple. Don't overthink them. A half-life is just the amount of time it takes for half a sample to undergo decay. To practice half-life, please do page 17 in your packet. Pause the video and work on page 17. Another thing that I wanted to clean up was what we did in lab. In this lab, we had 2 reactants that reacted, A and B, let's say. And they gave us some product. But remember, when we talk about kinetics, we are focusing on the reactants. In the lab, we made one of these reactants in such a massive concentration that it never really changed. So in the lab, we made A so massively concentrated that it was only B that was driving the reaction. This is known as swamping. So the rate of the reaction is really only driven by reactant B. Since we only have one reactant, we use our lab data and the integrated rate law to determine the order of the reaction with respect to one reactant. One final note to clear up was how catalysts work. Catalysts lower the activation energy by providing an alternative pathway for the reaction to occur. Biological catalysts hold our reactants in such a way that they have to collide, and therefore they lower that activation energy. But overall, the change in energy of the reaction is unchanged. The heat of the reaction, the difference between your products and your reactants, this change in energy is constant, no matter whether you have a catalyzed reaction or uncatalyzed reaction. The catalyzed reaction, again, simply lowers the activation energy. This means that whether the reaction is proceeding in the forward or proceeding in the reverse, a catalyst does not affect how fast. A catalyst does not affect equilibrium. It affects how quickly you arrive there. So when we talk about catalysts, we can say they are homogeneous or heterogeneous. A homogeneous catalyst is in the same phase as the reactants, so all gases or all solids, while a heterogeneous catalyst would be in different phases. So one of the examples that we started with, that water can produce hydrogen peroxide in the presence of platinum. Platinum is a solid metal while water is a liquid, so that is an example of a heterogeneous catalyst where they are in different phases. Now you can recognize a catalyst in a mechanism because it will be something that you start with, it'll be a reactant, and then become a product, while intermediaries start as products and then are immediately or later consumed. So here is the formation of hydrochloric acid. One possible mechanism is to conduct this experiment in the atmosphere around us, which has nitrogen and hydrogen gas in it. By adding chlorine gas, they make ammonium chloride. That ammonium chloride then breaks down into ammonia and hydrochloric acid. The ammonia immediately falls apart back into hydrogen and nitrogen gas. So in this mechanism, let's label our intermediaries and catalyst. An intermediary is something that is produced and then consumed. So this ammonium chloride is produced and then consumed, so it is an intermediary. And same with ammonia. Ammonia is produced and consumed, so it is an intermediary. However, nitrogen gas starts as a reactant and is later produced. It's not actually in the reaction, it is simply catalyzing it. So ammonia in this example, or in this mechanism, is a catalyst. We're also asked to show how this mechanism matches the stoichiometry. When we match the stoichiometry, you simply add everything up, canceling things that are products and reactants. So nitrogen, ammonium chloride, ammonia are all canceled out, as well as 3 of our hydrogens. So in the end, we end up with a mechanism that is valid by stoichiometry. It matches the stoichiometry of the reaction. Now, with that being said, we are done with Unit 5. I will see you all in class for your Unit 5 test. Next unit, we will tackle equilibrium.